Hello and welcome to AIST's 11th Decarbonization webinar. My name is Charlie Bender and I'm a staff engineer here and would like to have a couple of quick mentions for our audience today. Today's topic is challenges around synthetic hot metal coming from smelters and is organized by the AIST Decarbonization Subcommittee. AIST has several webinar guidelines. Each of your audio in the attendee room has been disabled, and we encourage you to put questions through the Q&A feature of this teleconference. The host and moderator will determine which questions are presented to the presenter, and all questions will be recorded for answer later if not answered during the presentation. We are recording this session, and it's available in the future at AIST's website. We do not encourage photos or recording of this presentation. If you have any technical difficulties during the webinar, please use the following email address, training@aist.org. AIST has two guiding antitrust and anti-harassment guidelines. Please carry forward with both of these in mind. Again, the questions for each presenter should be submitted through the Q&A feature of the software, and technical problems at the training@aist.org website, email address. The Decarbonization Subcommittee has been active. As mentioned, this is the 11th in a string of presentations from a lot of different topics, all focusing on the latest decarbonization topics in the industry. I'd like to take a minute to introduce our first moderator, Mike Grant. And Mike is working globally to lead Air Liquide's tactical and long-term strategies geared toward the steel industry. He started his career in 1988 working in iron making for Inland Steel Company as a blast furnace process engineer. Nearly 10 years later, at the end of 1997, he joined Air Liquide to develop and commission burner and oxygen injection systems for electric arc furnaces. In 2001, when Air Liquide purchased American Combustion, he began working for ACI, designing and commissioning oxygen injection systems for electric arc furnaces. He has designed successfully, commissioned, and optimized more than 30 EAFs worldwide. In 2007, he was transferred to Air Liquide Research Labs just outside of Paris, France, to continue working on EAF and blast furnace topics, most notably the European Commission ULCOS project, ultra-low CO2 steelmaking, where he was on the European team developing the top gas recycling blast furnace, and he now lives and works in Frankfurt, Germany. Our second moderator is Dr. Felix Fischbach, who studied metallurgy at RWTH in Aachen, Germany. He was the R&D lab manager and global steel expert at AIST, centered in Belgium. In 2021, he joined Bayerische Group in Germany, where he is head of consulting and drives decarbonization consultancy solutions for mini mills and integrated steel plants. He is vice chair of the AIST Decarbonization Subcommittee and officer at large of the European member chapter. Felix gives lectures at RWTH Aachen and has more than 50 publications, is owner of one patent, and was honored recently with the Charles H. Erdy Jr. AIST Award in 2023. Gentlemen, I turn the presentation over to the moderators.
Thank you very much, Charlie. It is my pleasure to introduce the first speaker, Gerald Wimmer. He's the Vice President of Converter Steelmaking at Prime Metals Technologies. He specializes in developing and optimizing steelmaking processes, leveraging simulation-based verification, and providing consulting for greenfield and brownfield projects. With a strong focus on innovation and sustainability, his work continues to drive efficiency and advancement in the global steel industry. From there, please welcome Gerald Wimmer.
Thanks, Mike, for the kind introduction. I will share my screen with you. Just a quick check. Can you see my screen in full presentation mode?
Yes.
Excellent. And let's get started with today's topic, synthetic hot metal from the smelter. As this is quite a new topic, the smelter, I think it's a good investment to spend some minutes in an introduction. Why are we doing all this? It is getting easier? No. It is getting cheaper? No. The only reason why we are entering these new fields, and we will see later, there is quite an R&D effort necessary to prove all these assumptions. There is quite the change in the steel plant coming up, are the CO2 emissions. And that's why I always like to start with these slides, which all of you know in the one or the other form, which is simply summarizing the way that we can make steel. And if you look on the very first line, the dominant way steel is produced today via the integrated blast furnace route, we have to say this is the best, most efficient, cheapest way to make iron steel, but it has very high CO2 emission, as we can see here on the orange bars. And only due to the move that our society decided, and I think this is a very important move, and it's questionable if we are moving fast enough. But in order to do this move, we have to find solutions to reduce the CO2 emissions. Carbon capture and storage for the blast furnace could be one option, but seems not to be the most promising one. That's why we end up, after recycling, using all the scrap available in the electric arc furnace, still using the iron ore for iron production, ending up in direct reduction, feeding into an electrical furnace. And the common way we do this today is just classical direct reduction, today mainly shaft technology, feeding into an electric arc furnace. Why can't we do this on a large scale? Because there is a shortage in the iron ores. And this is the second message I would like to convey with you. The electric arc furnace is proven solution and the simpler solution to use direct reduced material and make steel out of it. But the electric arc furnace needs high-grade iron ore. You can see here a global map of the iron ore shipped around the world, an incredible amount of 1,500 million tons. On the vertical axis, you can see the iron content of this ore, in yellow the gangue, and in white, of course, the oxygen that's bonded to the iron oxide. And we see we have here excellent iron ores with very low gangue content, and other iron ores of lower grade with much higher gangue content. If we charge all of them to the same electric arc furnace, we see this very high-grade iron ores. They fit very well to the electric arc furnace because they end up in reasonably low slag amount of some 180, 200, 240 kilograms. While the other iron ores, and mainly the iron ores here in the center, almost all the Australian iron ores belong to this section, would lead to a very high slag amount in electric arc furnace, and high slag amount in electric arc furnace always means low productivity and low yield. That's why today we are fine. These low-grade iron ores are used in the blast furnace. The electric arc furnace guys use the high-grade iron ores, and also important to remember, they are willing to pay this DI premium. So these high-grade DIs are sold by the miners with a higher price, and there is even a market index for this. And the electric arc furnace guys are happy to pay this premium because this makes the operation of the furnace cheaper. In future, if we manage to do the green move, blast furnace will not stay in a large scale. Mine application might remain with carbon capture and storage, but in the large scale, they have to be replaced. And for this one, electric arc furnace will not be the ideal solution. So for this low-grade iron ores, we will need a different solution, two-step process using a smelter and a BOF converter. And that's basically the idea of this new furnace. We split in two steps, and in this furnace, we just do melting and final reduction. So as I always say, my colleagues from direct reduction never complete their work. There's always some iron oxide left, which we still would like to get into metallic iron. So this final reduction and the melting is done in this new furnace, which we call smelter. For refining, we use the existing refining aggregates, if available, the BOF converter. but it requires to operate 2 aggregates. So the last point for the introduction is a cost comparison. Does it make sense to run 2 aggregates instead of 1? And we have made this process calculation as we are a bit lazy just for 2 grades. So a low grade iron ore with 62% and a high grade with 67%. And if we just now look on gray on the electric arc furnace, we see for the electric arc furnace, it's getting cheaper, my total costs, if I use high grade iron ore. So if we spend more money for high grade iron ore, the operation costs for the electric arc furnace, mainly electricity, lime, and yield losses, are decreasing a lot. And at the end, it's getting cheaper if we use this high grade iron ore. And this, I think, reflects well what we see on the market. There are already several plants operating direct reduction shaft, feeding directly into an electric arc furnace. And all these plants are using high-grade DI. Basically, all direct reduction plants today are producing high-grade material. When we look now at the 2-step process, smelter plus BUF, and calculate here cost again, the costs for both aggregates, we see, of course, also here, high-grade iron ore is more expensive than low-grade iron ores. But in total, we see that the costs are decreasing. So for the smelter, it's better to benefit from cheaper raw material. And that's the principal idea of this 2-step process. Let's use cheap raw material and save costs here. And that's why we see a clear separation of the market. High-grade iron ores will go to electric arc furnace, or in other words, each new electric arc furnace built today will require high-grade iron ores. While the low-grade iron ores, which today mainly used in sinter plant blast furnace, better go to the smelter. What does this predict for the future market prices? We see a lot of electric arc furnaces built at the moment. We see a lot of direct reduction plants built, so the demand for high-grade iron ores will go up in future for sure. So the price difference between these low-grade ores and the high-grade ores will increase in future further. So that's why the competitive advantage of the smelter, using cheaper raw materials, we predict that this advantage will increase in future. And it's not only our idea, there's a very recent nice paper from the Australian guys. Australian is having a lot of iron ores. Most of the iron ores is today going to the blast furnace. So of course for the big mining companies and the shareholders, but also for Australian society, there's a big question, what's the value of our iron ore in future if blast furnace has to be replaced by green alternatives? That's why there is a lot of R&D and also demo furnaces going on in Australia. And one of the recent papers was just published, you can find on the web. It's basically showing the same, that for low-grade iron ores, the smelter is cheaper than the electric arc furnace. For high-grade iron ores, it's turning around. That's principal introduction, why we are developing this new process, why we think it's necessary to do so. And now we would like to go a bit more in detail and look what is the result of the smelter. So what material do we get out? And what is the difference to the blast furnace? And before we go to the details, we should have a look how the material is produced in such a furnace, because this will of course affect the material properties. And here you can see a very simplified process picture how such a smelter is operated. One important thing, and that's very different to electric arc furnace, we have no arc formed between the electrode tip and the metal bars. We have either short arcing, so-called brush arc, between the electrode tip and the slag bars, or we operate the furnace with immersed electrode, where we just have resistance heating of the slag. We have a very big slag bars in the furnace. We need a certain slag height to have the slag resistance here, and we have a very big pool on hot metal in. We charge material, of course, we charge material to the electrodes because their temperature is highest. If we have arcing, some radiation is present, then we melt more materials, but we also charge material to the side walls. This is done to protect the refractory, to support the formation of a freeze layer, and to increase the refractory lifetime. These furnaces are so big and have hundreds of tons of metal and several hundreds tons of slag in, so it's quite an effort to drain such a furnace and to do maintenance of the refractory or relining. That's why, similar to submerged arc furnace, these furnaces are designed with a very wide bars, so very big distance between the process zone, the arc, and the wall, resulting in a low refractory wear index and consequently in a very long refractory lifetime. And the idea is to operate this furnace stable for very long time, several years, and try to get relining or partial repair only in an interval of several years. So that it's one of the unique features of this type of furnaces. As already mentioned, we have two ways of operation, either just immersed mode, as we can see here on the right, so pure resistance heating of the slag, making the slag hot and then melting via the hot slag the feed material. As the slag is not a very good heat conductor, the productivity might be too limited. That's why we always design the furnaces in a way that we also can run brush arc up to 50% power input via the arc. And always then we have in series the resistance heating of the slag another 50%. And here the radiation is supporting then the melting of the material. But of course, we also have much higher temperatures here, which will be a topic and has an effect later when we discuss the silicon. When we go now a bit more into detail, just focus here on the right side when we look here in the detail in the melting zone. So how is this working? The feed material is resting there in solid state. It's floating on the slag. So what the electric arc furnace guys call iceberg, and they do not like, we would like to have here. So we on purpose cover the slag surface with feed material, and then we melt this feed material with the arc and the hot slag. By melting of the DI pellets, we get droplets. These droplets get in contact with carbon. The carbon is charged with the DI and it's floating on top of the DI. And by this contact, the metal droplets get carburized and then sink down as carburized to the metal bars. And we adjust the carbon level by the amount of carbon we add to the furnace. So the more carbon we add, the thicker is the carbon level here. The more contact we get between the FeO and the carbon for reduction, and in the next step between the metallic iron droplets that we have formed and the carbon, and the more we carburize. So we can adjust the carbon level of the hot metal by the amount of carbon we feed to the furnace. Second reaction that's taking place is, of course, reduction. FeO reduction is easier, so this will happen first. So in principle, we will reduce first the FeO and then the silicon. But as we have very high temperatures here, there's always two both reactions running in parallel. And last but not least, there is some minor sulfur removal going on. Let's start with the first one, with the carbon. Here, a quick overview of our different carbon levels of DI. So today's direct reduction plant, all are running with natural gas, having typically a carbon level of 2.5% of carbon in the DI. And as we have a two-step process, we need a metal from our smelter that has sufficient carbon for smooth BOF operation. And this depends, of course, on the plant. What is the hot metal logistic? What is the hot metal temperature I can still achieve to get charged to the converter? What is the final tapping target from the converter? What's the size of the converter and the specific heat losses? Typically, we start about 3.5% of carbon. For a smooth operation, 4% is, of course, easier. And if we consider some 3.5%, then we see we need about 42 kilograms of coke to be added to the furnace. Part of it is used to increase the carbon level of the bars. Part of it is used to make the final reduction. And part of it is, of course, losses because yield is high, but not 100%. And if we in future switch to pure hydrogen production in our direct reduction plant, then of course the DI has almost 0% of carbon, and consequently the carbon amount that we have to charge to the smelter has to be increased. But regarding carbon level of the hot metal, the smelter is quite flexible, so we can adjust. What we cannot achieve is saturated, because for saturation in carbon, we would need very long contact of the carbon and the metal. And in this process zone where this carburization takes place, the reaction time or the time where we have contact is limited, so we will not have a hot metal saturated in carbon. So compared to blast furnaces, this is the world where most of us are coming from, and this we know very well. On blast furnace, we have this burden in the furnace where always carbon is present, and the metal therefore is always saturated in carbon. The hot metal from the smelter has slightly lower carbon content than the hot metal coming from blast furnace today. What is the consequence? Just having a look on the right picture here, we have done calculations for typical BUF converter, 0.04% carbon at tapping. Of course, the lower the carbon content in the pre-melt, the shorter is the blowing time. So while today, from this example, we had some 15 minutes pure blowing time, we would go down to 9 minutes if we just have a carbon content of 2.3%. Might sound good for the steel plant operation because the converter is getting faster and you are more relaxed and less a bottleneck in the production. Disadvantage is, of course, we need sufficient blowing time because we have to form the slag. We have to make sure that the dephosphorylation takes place. So we have to make sure that we purge all the nitrogen. So a certain blowing time we need in the converter for a stable process. That's why typically below 12% might get critical. And same is, of course, for scrap addition. The less carbon we have, the less carbon we combust and the less energy we produce in the BUF converter. So that's, of course, less cooling material we can charge to the furnace, meaning the scrap rate that we charge to the furnace is reduced. And that's why, for sure, if we change for a synthetic hot metal for the smelter, the scrap rate on the BUF converter needs to be adjusted. For all plants that go into a transition phase, having blast furnace and smelter operated in parallel, this is, of course, a classical example where a powerful process model on the BUF converter makes sense, that you really heat for heat, depending on the raw material you get, either it's from blast furnace, saturated in carbon, or from smelter, lower in carbon, or a mixture of it. You can precisely calculate the amount of scrap that can be charged to achieve the tapping temperature. We also tested this one. So dust carburization is a simple set of work by just adding the carbon from top. So this is a picture of our demo furnace, small electric arc furnace with 3 graphite electrodes. And here you can see an infrared picture of the process. These are the DI pellets we charge. This is 1 electrode. And when I play a movie, I ask you, have a look on the area around the electrode. So we see here these feed piles, they're melting very slowly, while all the feed material that's getting close to the electrode is melting quite quickly. This is what I've shown before. So this is this process zone where we have higher melting rates and high activity, while in the rest of the furnace we cover the bars to reduce radiation losses and protect the refractory, but much lower melting rate. And here we can see some results. Just focus on this one, the carbon content. So we have done several campaigns and measured the carbon for different charging rates, and these results are now plotted as a function of the material charged to the furnace for different campaigns. So it's quite a small furnace. We could do in maximum 1,400 kilograms of charging materials before we had to tap. And you can see here the carbon levels fluctuated a bit, but in average we could achieve 4.1% in carbon, which was more or less the value that we calculate. So first point check, yes, we can carburize the metal by simply adding carbon and charged carbon together with the DI, and the carburization then takes place during the smelting and reduction. It's not necessary to inject the carbon to the metal bars, which of course saves a lot of costs. Second point is sulfur. How does the hot metal from the smelter compare to the hot metal from the blast furnace? And of course, sulfur is not a lot of sulfur is in the iron ore. Sulfur is mainly coming from the carbon, meaning coking coal or pulverized coal we inject that we add to the process. And that's not a big difference. On the blast furnace, we need about 500 kilograms of coke per ton. On the smelter, we need, as I've shown in the last slide, depending on the direct reduction plant, natural gas based or hydrogen based, but typically we start at some 50 kilograms per ton. So we have about 1/10 of carbon that we add to the process, meaning the sulfur input is also only 1/10. Second topic is then the participation factor. Where is the sulfur growing? Does it report to the metal or does it report in the slag in our aggregate? And there we see the partitioning factor for the smelter is about half to 1/3 of the factor from the blast furnace, meaning for the smelter, due to the different reducing atmosphere, the different kinetics there, more sulfur is reported to the slag, but we have less sulfur input. That's why typically on average we could say in the smelter we have about 1/3 of sulfur content than we have on the blast furnace. Still, we have classical hot metal logistics. So if necessary and if very low sulfur content for the final product is required, hot metal desulfurization is also possible to be done with the hot metal from the smelter. And as the level of sulfur is much lower, the consumption figures for the hot metal desulfurization, also the treatment time is expected or is definitely significantly lower than it is today when we have to desulfurize hot metal from the blast furnace. Silicon, next topic. So silicon is coming, of course, from the gangue. There's a lot of silicon oxide in the gangue, and this can be reduced. How much of the silicon is reduced is, of course, depending on the reduction power. And there, of course, if we have this arcing, in the arc zone, we have enough temperature and carbon available to reduce silicon. But there is always a competition between the FVO and the SCO2. So always first, the iron oxide is reduced, and secondly, the silicon oxide. And second point is we have here a big interface between metal and slag. So this furnace is very big. We have very long residence time. So the material has quite a long time to get in equilibrium. That's why we have plotted here typical equilibrium values calculated with stacked stage. So we asked if we have a metal rich in carbon and a slag rich in SiO2, what would be the equilibrium value of silicon in the metal, and calculated this for different basicities. And we see it's temperature dependent. The higher the temperature, the higher the silicon. For a temperature of 1450, for example, for the slag and a basicity of 1.1, the equilibrium would be somewhere at 0.4% of silicon. So that's why for the silicon level, we expect that the levels are quite similar to what we see today on the blast furnace. The last two elements I would like to address is nitrogen and phosphorus. So nitrogen mainly we get for the contact with the ambient air. Where do we have such contact? Inside the furnace, we have a reducing atmosphere. So the furnace is completely closed. There is no burner and also minor increase of ambient air only. So there is almost no nitrogen contact inside the furnace. But of course, when we do the tapping, classical tapping from the tap holes and then run us into the torpedo cars, we get some contact with ambient air and we will have some pickup of nitrogen during this tapping. The maximum from solubility point of view, nitrogen content that this metal can get is about 170 ppm. The purging of the nitrogen in the BOF converter works like it works today for blast furnace. So that's why we expect for the crude steel that we tap from the converter later, we will see similar values from nitrogen as we see today for hot metal coming from the blast furnace. And last point is phosphorus. For phosphorus, it depends a lot on the mineral fraction if reduction of phosphorus in the direct reduction plant takes place, or if these minerals are strong enough not to be reduced. And depending on this mineral fraction, it can be that we have similar phosphorus levels than on today's blast furnace, or slightly lower ones if the mineral fraction is too strong to be reduced by the direct reduction plant, which has, of course, a much lower reduction power than the blast furnace. Blast furnace always has metallization degree of 99.99. Direct reduction plant, depending on technology, somewhere at 90%, maybe only 85%. And of course, in such cases, we will not reduce all the phosphorus, and part of the phosphorus is already reported then to the slag in the smelter. So I hope I could provide a brief overview of what we expect from this new furnace, from the hot metal coming from this new furnace. Quickly summarizing it, this metal is rich in carbon but not saturated. That's why we struggle a bit to call it hot metal, because hot metal is defined as a metal that's saturated in carbon. And that's why also for the title of this webinar, we decided to call it synthetic hot metal, with the main difference slightly lower levels in carbon than blast furnace. And we can decide the level of carbon, silicon level similar to blast furnace, sulfur level lower than blast furnace, nitrogen level and phosphorus level similar to blast furnace. If there are any questions, I'm happy to answer them.
Thank you very much, Gerald. Excellent presentation. We're going to answer all the questions at the end after the second presentation. And with that, I pass it on to Felix.
Thank you.
Thank you very much, Mike. And thank you very much, Gerald, for the great presentation. So our second presenter is Jisa. He's a metallurgy specialist at Hatch with 14 years of research and professional experience in North America, Asia Pacific, and Africa. His areas of expertise include low-emission electric iron and steel processes, techno-economic assessment for capital projects, development, and commissioning of innovative metallurgical processes, as well as value and use analysis and optimization across the full iron and steel value chain. And with having said that, I invite you to open your camera and please start your presentation.
Thank you very much, Felix. Let me share my screen. Please let me know when you can see it. Can everyone see my screen?
Yes,
Yes.
it looks very good.
Okay, perfect. Thank you very much, Felix, for the kind introduction, and thanks AIST for organizing this, and appreciate Gerald giving a very good overview of the smelter, melter, or electric smelting furnace process. Again, today the topic of the talk is understanding, optimizing the properties of what we call synthetic hot metal in electric smelting furnace. That's what we refer to these equipment as. Again, Gerald has done a very good overview of why this process exists and these where does it fit in the value chain, but I'll just do a quick recap. Again, traditional steel making is done in two major pathways: integrated steel making up top, which is lower grade iron ore, whether it's sinter, lump, or BF grade pellets, plus coke, turned into iron in the blast furnace, goes through basic oxygen furnace steel making. Again, using widely available iron ore, but unfortunately coming with quite a bit of a GHG emission cost. On the other hand, you have the mini mill based steelmaking routes. We're using high quality raw materials such as DR grade iron ore, as well as scrap, and using lower emission reductants such as natural gas or hydrogen, making DRI, whether it's hot charge or not, turning into steel in the EAF steelmaking process. Much lower emission, but unfortunately has some constraints, whether it's the availability of low emission reductants, but more importantly, available of high quality iron ore in particular, which again, is quite well understood. Where the ESF fits in is sort of a third way in the middle path. It is using widely available, typically BF grade iron ore. Today it's mostly in the pellet DRI form, but certainly sinter fines, fluidized bed-based iron making processes are compatible as well. And using electric smelting furnace or smelter or melter or electric melting furnace, turning into hot metal, or in this case, sometimes we refer to the synthetic hot metal, or sometimes called the green hot metal, for use downstream in steel making. Now that of course can be used as hot metal inside the BOF, can also be turned to pig iron for use in the EAF. The hot metal doesn't discriminate. Again, coming up to a comparable level of emission as EAF steel making, but using much more widely available iron ore. Therefore realizing cost savings and unlocking value and use benefits. So I'll go straight into the chemistry components. So what are when we talk about hot metal chemistry, the four biggest factors or elements we usually talk about is carbon, silicon, phosphorus, and sulfur. Carbon, silicon, of course, provides energy, whereas phosphorus and sulfur are more of a quality factors impacting steel making. Both carbon and silicon provides a lot of energy, and carbon especially, it's a primary energy source for BOF steel making, allows higher scrap use, does a lot of the refining in the BOF, and of course has a lot of benefits when used in the EAF as well, whether it's in energy benefits, as well as allowing effects like slag foaming to improve the quality and the efficiency of steel making. Phosphorus and sulfur, on the other hand, are impurities that needs to be removed. They come from different sources, but all of it needs to be removed for steel to finally meet the quality specifications. Again, silicon is an interesting one because it provides energy, which is good. Some BOF operators prefer to have some silicon to allow higher scrap usage. But again, because SiO2 is a slag component where CO2 is a gas, using silicon as an energy source in a hot metal, which unfortunately generates a lot more steel making slag. And that's actually one of the reasons driving why EAF efficiency comes down significantly with the presence of gangue material like silica. So we'll go into a little bit about the fundamental drivers for the differences in hot metal, let's say, characteristics. So I think the first is a little bit more philosophical. I think it's, as we explained earlier, it's a DRI process plus an ESF to replace an entire blast furnace. The virtue of simply separating an entire blast furnace process, which everything from preheating of the burden, reduction, melting, and separation into two separate processes allows independent control of those two separate processes. Now, in the DRI shaft furnace, the preheating is done, majority of the reduction and metallization is completed, and the hot material is charged into the ESF, where it undergoes complete reduction, metallization, melting, and separation into two different phases. So while if you want to do all of these processes inside the conventional blast furnace, requires very careful and simultaneous control of all of these various parameters to make your hot metal that's on spec. The DRI ESF, the separation to two separate processes allow better independent and separate optimization of the separate processes, therefore giving you more control and opportunities to optimize and control the quality of the hot metal that's otherwise not possible inside a conventional blast furnace. So looking a little bit closer at the process itself, again, on the left-hand side is a typical blast furnace, and of course the ESF process is basically analogous to the lower half of the blast furnace. We're very so there's a lot of similarities. We're very strong reducing environment at very high temperature. So the first burden completely metallizes, completely reduces, melts and separates into two different phases of metal and slag, and collects it into the hot heel at the bottom. The ferrous material typically used is very similar, typically lower grade ferrous burden, like BF grade pellets. And again, that's because both the blast furnace and the ESF are excellent at handling large amounts of slag and very effective rejecting the gangue and completely metallizing the hot metal. Whereas the DRI process does not reject any gangue and does not completely metallizes the ore. Again, similarly, both the blast furnace and the ESF have a lot of process advantage. They're both continuous operations, have very high availability, and extremely long campaign life as measured in a number of decades. Of course, there's a lot of differences as well. The big fundamental driver is the difference in the source of energy. So whereas blast furnace is predominantly chemically driven, all right, it's coke and hot blast and PCI or whatever energy source you inject into the furnace. But the ESF is predominantly electrically powered. So again, whether it's arc heating or resistance heating through the slag, majority of the power comes from electricity. Therefore, there is an advantage in the electric smelting furnace that allows much faster reaction and more precise control of the process, whereas the blast furnace burden descends and completes the reaction in the order of multiple hours, 6 to 8 hours, if not more. The ESF process, the residence time, as well as the ability to control the process through direct intervention, slag chemistry, or direct control of the furnace power input, allows much faster and precise control of both the heat and mass balance of the process. Again, offering very rapid and precise control, which again has a very positive impact on the consistency and quality of the hot metal we produce at the end. Again, this, of course, coupling with the much larger hot heel, even larger than the blast furnace on over 1,000 tons at the bottom of the ESF, certainly allows much more consistent product quality, which a BOF operator will certainly appreciate. As we know, blast furnace hot metal quality swings can be quite detrimental to a consistent and steady BOF operation. Again, as we've understood, there is no such thing as a dead man inside the ESF, that giant mass of carbon, whether it's floating or sinking, that carburizes the hot metal to saturation level. That does not exist inside the ESF, and therefore, of course, as the previous presentation mentioned, the hot metal is not expected to be fully carburized to this level of saturation. So a little bit more about the background of this process. So what are all these understandings, our understanding of the process and hot metal quality of slag engineering comes from? Again, this is not a very well-known fact in the steel industry that iron making electric smelting furnace has been around for many, many decades since the beginning of the 20th century. And certainly Hatch has supplied many of these furnaces operating for the past 50, 60 years or so. There was and still are a lot of commercial electric iron making furnaces around the world, Highfield New Zealand Steel and many Rio Tinto furnaces out there. Again, what this proves is that electric smelting furnace iron making is entirely doable on the commercial scale and can reliably operate and produce hot metal that's on spec, certainly at the right level of consistency and reliability for a commercial iron making furnace. Of course, through all these experiences, we've dealt with a variety of different iron ore feeds, slag chemistries, product specifications. So we do understand how electric iron making process control and the quality of the iron that's produced from it and how to control it. Second of all, beyond just iron making electric furnaces, large, by large, I mean probably close to 100 megawatt furnaces are very widely used, again, in the ferroalloy and non-ferrous applications. These are scale-wise will be equivalent to about 1.5 million tons of feed throughput a year, which is at the scale that the steel industry needs to apply this solution. Again, there's been complete smelter solutions offered for our history, and of course through for the entire metallurgical industry to prove that all the not just the furnace itself, but all this entire solution from off-gas system to raw material handling are available. And of course, all the strategies to implement this in reliable and consistent production and quality control is very, very mature. Again, just like Gerald has mentioned, there's been a lot of pilot and lab tests on this subject. Again, from Hatch, we've been doing this type of test work going back to the mid-2000s. Smelting and melting experience and trials using commercial grade DRI, natural gas-based and carbon-free DRI, really to prove a lot of fine-tuning mechanism and control methodologies, as well as developing, implementing proprietary technologies to control a lot of these parameters, especially hot metal chemistry. And finally, we have been partnering with a lot of clients from the raw material suppliers all the way to steel makers in understanding, designing these kind of furnaces, coupling with, again, trials and tests and analysis to really understand how to get to the exact hot metal specification that we like. I think one thing we can see from this experience, the ESF is a very versatile tool. It can be used to produce everything from iron to nickel and handle a wide variety of feed material to produce all kinds of hot metal specifications. So really fine-tuning, understanding how to produce each of these and designing a furnace to do that, I think is quite important and contributed a lot to our understanding of the hot metal production from ESF over the years. So here's a quick summary of what we think a typical ESF hot metal compared to typical blast furnace hot metal. So synthetic hot metal is better than conventional hot metal, just like synthetic motor oil is. Maybe there's certainly differences. So I think I'll echo Gerald's presentation. Hot metal carbon is probably the most obvious difference. It's not going to be saturated like blast furnace hot metal, 4.5%, but certainly in the high threes and even low fours is achievable and demonstrated. Silicon level on average is comparable to that from the blast furnace, but we expect it to be much more consistent level of silicon. Again, that provides significant operational benefits compared to traditional blast furnace operation. Things like sulfur, we expect to be much lower by virtue of simply having much less sulfur load in the input. And slag rate, I think it's a very important one, although it's not part of hot metal, but it does affect everything about hot metal. As we know, most processes, once you fix the slag, the process tend to be able to run itself fairly well. When we use typical BF grade iron ore, depending on, of course, the acidity of the pellets, the fluxing strategy, the slag rate in the order of 100 to 220 kilogram per ton of hot metal. But of course, when you use higher and higher grade DRI, that number can become well below 100 when we use DR grade DRI in this application. So we'll go into a little bit into each of these elements. Again, I won't go into the exact dynamics of it, but more about a practical experience we've done working these furnaces over the decades. I think the number one question, of course, carbon. Without a dead man, ESF hot metal is not expected to be fully saturated. But our tests have demonstrated when we use typical DRI, commercial grade DR, achieving well above 3.5% carbon hot metal is doable. And we've been testing a lot of proprietary technologies and furnace design tools to enhance that, and some have proven quite effective. So 3.5% or more is certainly doable. And on the matter of silicon, the general conventional thinking is a higher arc temperature will likely encourage the reduction of silica to recover more silicon in the hot metal. Again, but I think based on our experience on these things is that unlike the blast furnace, the correlation between hot metal temperature and silicon in the hot metal is not as strong. And it is possible to very precisely control the silicon content in the hot metal through very precise feed and slag practice controlled engineering. And depending on the end user preference, it's possible to be adjusted. For example, creating a higher hot metal, higher silicon hot metal for BOF to use more scrap, or much less silicon to allow easier dephosphorization downstream. All of these are possible. And again, in general, by and large, the silicon content is comparable to blast furnace, but it's much more consistent level of silicon that really provides the benefit. Again, down to the temperature, again, because of the electrical control of the energy balance, temperature of the slag can be controlled and adjusted very quickly, which not only makes the overall control of your process much easier, it also allows precise control of slag without upsiding the entire iron making process like the blast furnace. Again, blast furnace, you don't really directly control the slag quality or the temperature. It's more about the recipe control and with some control in the fuel rate, which again impacts your slag make, for example. So very precise control of the slag temperature and composition is quite difficult, but that's again something that can be very precisely monitored and controlled in the ESF that provides all these other benefits to the hot metal quality. A little bit more on the sulfur and phosphorus side of things. Again, sulfur removal capacity of the ESF is comparable to the BF in general, depending, of course, precise slag engineering. The net input of sulfur is significantly lower. Therefore, we expect the sulfur content of the hot metal to be significantly lower than that from the blast furnace. Of course, this is subject to the choice of reductants, additives, reverts you add to the electric smelting furnace, but in general, will be much lower and require a lot less desulfurization, and perhaps even for some very less stringent grades of steel, desulfurization may not even be necessary. Phosphorus is similar. The removal capacity is comparable to the blast furnace, and it's highly dependent on the ore selection. And well, dephosphoralization is a very strong function of both temperature and slag property. And since we can control those parameters very precisely, it provides a lot of opportunities to enhance phosphorus recovery or through optimizing both the slag and the process. Opportunities such as, can we make very low phosphorus ore from relatively high, very low phosphorus hot metal for pig iron that can be used in the EAF from relatively higher phosphorus ore. All of those are applications that can be precisely engineered through process design and slag engineering. Again, I'll stress a little bit more about the process control aspects. I think hot metal optimization, the use of synthetic hot metal is beyond just the chemistry. I think I would like to emphasize the influence or the ability to directly control the process, intervene on the mass energy balance on the overall consistency of the hot metal and the benefit that can bring to the overall melt shop, hot metal and the BOF or steel making. I think the mass and balance control of the ESF is much easier than the blast furnace, which is again usually limited by the burden recipe and fuel rate control. And often comes with significant emission impacts and so on. So the separate tapping of metal and slag in the ESF also eliminates slag carryover. That's an additional benefit, of course. And one thing that's usually overlooked is the scrap addition. So ESF can be designed to take up to 20% size scrap. So what that means is that, of course, there will be impact on the hot metal quality. But again, that will, I guess, deprioritize perhaps the need for fully saturated hot metal in terms of carbon. If you can use 20% scrap in the ESF, is there really a need to get a 4.5% carbon hot metal then to melt to additional scrap? Is there some sort of optimization application opportunity there where you use more of the scrap in the ESF and have a lower carbon hot metal for the BOF that allows your blow time to come down, for example? So a lot of opportunity to optimize the overall operation based on the characteristics of the hot metal we produce and the ability to control it. So operationally, in addition to it retaining all the benefits of the blast furnace, such as high availability, continuous tapping, long campaign life in order of 20 years or so, also had additional things like very quick turn down. Our furnaces have been proven to be able to be hot idle for weeks, if not months, multiple months, and quickly resume operation. Again, and a really powerful function that makes the overall operation of the integrated steelmaking and provides quite a bit of value in operation. And of course, the large hot heel inside the ESF allows a hot metal inventory to be built up or squeezed out, so to say, that adds an additional layer of process buffer and opportunity for simplifying of hot metal logistics if needs be. So let's take a look after the ESF itself. So just like blast furnace, the ESF hot metal or synthetic hot metal can undergo post tap treatments, things like hot metal pretreatment. Again, it's a very mature technology, possible to reuse whatever assets you currently have for a blast furnace. Again, the one example is the system that we provide, and we like to integrate it as our overall furnace solution, is a single stage and multi-stage refining, where inside a hot metal ladle, you can adjust sulfur, silicon, phosphorus, and carburize, achieve additional carburization if needed in a single stage and in multiple stages. Again, these are very mature technologies. It offers an additional lever to allow you to optimize your overall process from the selection of the ore to how you run your DRI and ESF plants, and additional levers adjustment you want to make before it goes to steelmaking. This is what the typical system like that looks like as well. If you haven't seen one of those. Again, quickly concluding, I think a three overarching comment to make. One thing is synthetic hot metal or ESF hot metal is pretty much same as conventional hot metal with a slight changes in chemistry. Just like for BOF need to adjust for blast furnace variations, steelmaking in general need to adapt to and learn and to use ESF hot metal effectively and achieve the right optimal point of operation. Is just no different from how typically you adapt to a different operation. But the main benefit of using ESF hot metal from an operation perspective, in addition to the quality and cost and emissions, is the consistency of that hot metal quality coming from the very powerful ability to carefully control and rapidly control the operation inside the ESF, and separating the DRI process into upstream process does not impact hot metal quality directly in operation. It is a very flexible process, can design for a variety of feed to provide a very wide range of hot metal specifications, and allows you the opportunity to fully optimize your value chain from ore to DRI to ESF with possible pretreatment and your steelmaking operation to unlock all the values and maximize the value in use. It's a very mature technology. Synthetic hot metal is the new OBM for high efficiency, high quality, and also lower emission steelmaking. And it fits very well into both BOF and EAF steelmaking processes. And there's the limit is only imagination in the way you can use this versatile process, replacing a blast furnace, producing pig iron for the EAF, recycle your waste and slags and fines and so on to replace the sinter plant capacity, for example. They're all quite possible and can be engineered for. Thank you very much. That's my presentation.
Well, thank you very much for another excellent presentation. And we have some questions that have been written down in the question area. So I guess I will start to read those out. And And then I'll pass the next question on to Felix. How is the ESF Cliffs planning for Middletown different from the ESF that has been described? They're planning to use DRI from blast furnace pellets, high gang, compared to DRI grade. What is the status of that project? Anyone have an answer?
Maybe I can comment a little bit. Of course, we can't comment on specific projects from steel makers, status of any of those. But again, in principle, just looking at the flow sheet, it is very similar. Again, I think all smelter or ESF applications follow a very similar flow sheet, right? Using lower grade, let's say BF grade pellets, turning to DRI, melting it, and feed a BOF operation to replace a blast furnace. So I would say that the flow sheet is definitely similar to all of these we presented today. But again, I think all of us, we can't really comment on specific project status, especially on behalf of an operator.
And the next question is from Anonymous, and it is, what is so possibly for both of you, what is the electrical consumption per ton of, I guess, hot metal of the ESF using either DRI from BF grade pellets or DR grade pellets, and how much reduction is possible if the DRI is charged hot?
Is it okay for you? I'm gonna start with an answer. So energy savings from hot charging is same like for electric arc furnace, and there we have evidence. So it's about 100 kilowatt hours per ton that you can save on electrical energy if you manage to charge hot with some 500-600 degrees. Energy consumption per ton of hot metal depends a lot on the metallization degree, on the reduction degree that your colleagues from the direct reduction plant already did. The more reduction work we have to do in the furnace, the higher is the consumption of electrical energy. That's why I can only give a range. It's somewhere between 600 kilowatt hours and 800-900 kilowatt hours. It's always higher than on electric arc furnace, because on electric arc furnace we have always the electricity, of course, from the arc, but a lot of chemical energy. For the smelter we do not have. For the smelter we do not have any chemical heating, no burners, no carbon injection, no oxidation. That's why we have pure electrical energy, and that's why looking at the pure electrical consumption figures, they're always higher on the smelter than on the electric arc furnace.
Yeah, I agree, Gerald. To that comment again, the average value is a little bit higher than we see for EAF because it's fully electric heated. And in addition to the metallization, another big factor is your slag design and engineering. Depending on what you put into it, a lot of our designs, try to maximize reverts. We put plant-wide reverts into the ESF and treat ESF as a sinter plant substitute to recover iron unit. That, of course, drives up the energy consumption significantly, but it derives value elsewhere. So it's not, again, electrical consumption is not a strict measurement of economics. I think the answer is that it really depends on what the furnace is designed for.
Okay, next question's from Pollyanna. How does the pellet residence time in the electroslag furnace compare to that in the blast furnace? And what are the factors influencing the difference?
In the blast furnace, of course, we have a much more burden feeding in, so that's why the residence time of the pellets in the blast furnace going all through the upper part of the blast furnace where they are heating and reduced before they come to the melting zone. This is very different to the smelter. So we have to see the blast furnace is the direct reduction plus the smelter. So if we compare both aggregates, the residence time might be similar. If we just look on the smelter, where we just have these small feed piles on it, so not too many tons of pellet material that's waiting in the furnace to be molten, then of course the residence time of pellets in the smelter is quite short, but it already had several hours of residence time in the direct reduction plant. So I think if we compare blast furnace smelter, this is a bit misleading. If we compare blast furnace, we should compare it to direct reduction step plus the smelter.
So I'll just pile on a little bit of a comment. I think with rather specific throughput time, I think blast furnace 6 to 8 hours typically. In the electric smelting furnace, much lower. But when you put into a process control and consistency perspective, process upset in the blast furnace may take a couple of days to recover, whereas that's probably less than a day or several hours to recover in the ESF. So even though the residence time is quite different, the actual impact and the cost impact on operation efficiency is even much more significant.
Okay, the next question here is, it says for Gisa, but maybe also for Gerald. For reaching more than 3.5% carbon in hot metal, how much carbon or coke has to be added in the DRI? And is there a carbon neutral way to bring in this carbon?
Maybe I'll go first. That's a great question. Again, of course, in principle, the higher the carbon that comes in the DRI, the easier it is to carburize. Of course, if it's not there in the DRI, you have to carburize with other reductant sources, additions to the ESF. There are ways, flow sheets that we're examining to incorporate, again, renewable ways of using, or certainly circular ways of adding carbon. For example, gas methanation, synthetic natural gas, going down to the DRI plant. Again, I think another comment is that the carbon at DRI is probably the most effective way of carrying carbon to the ESF. So if you can use synthetic or renewable natural gas to carburize, create a high carbon DRI that's low emission, that will be much more effective in principle than adding a lot of coal or reductant or anthracites to the ESF to achieve the same result.
Yeah, fully agree. What we also have to see is that the amount of carbon that we need is still there, but it's about 1/10 of the amount that we need from today's blast furnaces, so about 50, 60 kilograms per ton. So I see in the midterm future, this should be possible also be done by biochar. We have tested quite an amount of different biochars. All of them worked quite well. Yield was a bit different, but from process perspective, there is no argument why in the smelter we should not be able to use biochar for this carburization step.
If I may jump in about the carbon topic, in Gerald's presentation, he mentioned coke is used to put carbon into the hot metal. Given the fact that there's a slag between the charging materials and the hot metal, how easy is it to put carbon in the hot metal with the given charge materials that you use? This question is for both of you. Thank you.
As I mentioned in my presentation, there is no contact of the hot metal with the feed material, so we may have to manage to carburize the metal droplets during reduction and processing them. As soon as they sink down through the slag zone to the metal bars, the game is over, and we can only carburize with this emergency carbon injection lens, which is an emergency stuff because it's quite expensive to inject the carbon. So the idea is to carburize the metal droplets when they are formed on top of the slag zone, and they're not to dip the carbon into the metal bars, because this will cool the metal bars and would crash our temperature balance.
Yeah, again, I think I'll answer not as with the specific technology, but I think in general, carburization, there's a lot of different mechanisms to achieve it. And it's really in how you design the furnace, charging practices, selection of ore, and selection of the carbon source. Again, from a lot of experience we've done in the past looking at the iron making electric furnaces, achieving a high carbon content is, I would say, it's not a very high risk item. In the 60s, the electric iron making furnace from rotary kiln, which is even lower carbon than gas-based DRI, consistently reach about 4% in certain operations. Of course, operational style changes, but there are certainly design feature and control mechanisms we can incorporate in today's modern furnace design to achieve a very high level of carburization if needed.
Okay, the next question from Jennifer is there any sign that the industry will converge on a common terminology for what is currently referred to as smelter, ESF, OBF, OSBF, and various OEMs? At the moment, and I certainly understand there is some confusion.
maybe I'll just answer for it again. That's a very good point. But I think eventually depends. It might become just a LD converter, BOS, BOF nomenclature divergence that people will get used to. And maybe eventually, depends on OEM supply, different acronyms and the different supply package will have some slightly different features. But I think the overall process will resemble each other quite well. And sort of convergence will be in the process and the flow sheet, not necessarily in the nomenclature and the exact features of each OEM supply.
Okay, next question from John. Is it possible to use self-fluxed iron ore pellets and not add flux stone, dolomite, limestone, etc. to the EAF?
Yes, of course, it's possible to use flux pellets, but it's getting more complicated because, you know, the pelletizing plant normally tries to produce pellets that fits for everyone. So making flux pellets, flux for a specific furnace, for a specific customer is making the full logistics more complicated. And if you have to add a lot of fluxes, also stability of the pellets might get influenced. That's why today, typically, we do not see that much efforts anymore to flux the pellets, but everyone accepts it, and you're much more flexible if you do the fluxing directly at the furnace.
And I'll just add on that I think adding a flux pellets, which is again fixing your recipes further upstream, do take away a certain degree of precise and rapid chemical control. You can have it on ESF through direct flux addition and slag engineering control. So it is a balance I think you have to play.
At 6 minutes at the hour, we'd like to thank both presenters and moderators for producing yet another excellent decarbonization webinar. The AIST organization has the ability to follow the presentation in our announcements on the website. Here we show a couple of presentations that have just occurred in March and one coming up on the 20th. Furthermore, on this part of the website at this URL and located at this portion of the website, this is for where to find technology committees. This is a complete list of all of the decarbonization webinars, now approaching 11 in a row. So it's a curated list of just decarbonization webinars. AIST has a resource center. It now has in excess of 11,000 curated technical papers and presentations. Please go to that resource center as part of your search for technical information in the industry. Upcoming presentations, we've had a few completed in March in Louisville and Orlando, Florida. We have the Crane Symposium in Indianapolis in June, and later in October, now forming the Birmingham and again Louisville, Kentucky presentations. Of course, everyone is invited to come to Nashville, Tennessee between the 5th and 8th of May, and we do hope to see you there. Would like to highlight that Dr. Gisa is a panelist hosted by the Oxygen Steelmaking Committee on Wednesday, I believe. And so to come and ask questions again in person, please come to that session at AIST Tech. Thank you all for your participation, moderators, presenters. This presentation will be available on the AIST website within about 5 business days. Thank you all. Have a great day.